Okay, also today we have the pleasure to have Amin Rahimian with us. He received in 2016 the Master in Statistics from the Wharton School. And also recently he was the Best Student Paper Award finalist in ACC and also the finalist for the 2015 Facebook Fellowship. And in the past, also in 2004, he was the gold medalist in Iran's national chemistry Olympiad. So.
Thank you, Aziz. It's a pleasure to be here to present my work with Ali, my advisor. So today I will be talking about Bayesian heuristics for group decisions. Group decision scenarios are a very intuitive thing, so you don't need much introduction. Whenever, for example, a good example is a business meeting when different people are trying to come up with the best policy. They interact with each other, they exchange opinions. Each of them has some private information that is the base for their recommendations. And after interactions and after deliberation, they come up with a policy that they think is best. So to model this situation, arguably it is an important situation because many of the policies are the result of such interactions. So it is important to understand its properties, how people come up with decisions in groups, and what we can do to improve them, these decision-making processes. So to analyze them, one approach is to look at Bayesian decision-making, meaning that people will come up with the best opinion or best descriptor of their observations at every time and try to communicate that. So this approach has some drawbacks. First of all, it is unrealistic to assume that people would spend so much time and brain power in coming up with really optimal descriptions for their observations. Also, analyzing it would lead to problems because there you need to do Bayesian analysis in incomplete information settings because you don't have all the observations available to you. So you have to do Bayesian inference in settings where there are multiple unobserved variables. So you have to consider their possibilities too in making your decisions. And this leads to exponential complexity. That makes Bayesian decisions difficult to analyze. So the alternative is to rely on some heuristics for decision making. These kind of heuristics are observed in real life quite often, so using heuristics for decision making appears to be a good descriptor. For example, one very famous heuristic is averaging. In many situations, people, when they are faced with multiple sources of information, to aggregate them, they average them together. And this model has also been analyzed mathematically. So a famous work is due to DeGroot in 1974 in Journal of American Statistical Association. And there are works before that uses this averaging model for analyzing social power. Most famously is the work by French in 1950s. And there are many follow-ups. But the heuristic decision-making approach has also some drawbacks. Most importantly, we don't know why people should commit to any kind of heuristic and what is the base for using heuristics in decision-making. In this work, I will try to come up with a base for these heuristic decision-makings as one of my main goals. But before that, let's look more closely on what can happen in a decision scenario and what is the importance of analyzing decision scenarios. There are many inefficiencies associated with group decision-making, and they have been analyzed in social psychology and economics and other related fields of study. For example, groupthink is one inefficiency of group decision making that has been singled out. It refers to the fact that once a group appears to be in consensus on some policy, then contradicting that policy may become quite difficult, may appear as, may be interpreted as disloyalty, or basically the desire to reach a consensus or a harmony in group would sometimes lead to the group ending up with what is not optimal for everybody. Other examples are group polarization or choice shift. This refers to when the phenomena when people of like-minded about some particular issue, they interact with each other repeatedly and their opinions end up shifting to extremes. So originally they had maybe a bad opinion about a particular topic, but after interacting with each other, this enters a positive feedback loop, and they all end up having a very bad opinion about that particular thing. This is referred to as group polarization or choice shift toward more extremes. And also people usually come to this interaction with some biases, so people want to know how these biases would affect group decision process. And the analysis of these inefficiencies have led to advices, practical advices for group decision making. For example, there is a famous advice that says a good way to elicit information from a group of people is to individually and privately approach them and extract their opinions and then try to aggregate those opinions rather than letting them to enter a public discussion, because of, and it's exactly because of these inefficiencies that are associated with group decision making or public discussion. Or for example, to avoid groupthink, project pre-mortem is a practice advocated by Klein, proposed in 2017. It says that once a group has made a decision or has committed to a policy, it's a good idea to imagine a situation when that policy has failed and then try to write a report about the reasons of that failure. This will make questioning consensus easier and can help mitigate the effect of groupthink. So let's see how we will model this groupthink situation and what kind of insights our model gives us. So there would be a true state of the world that is basically representing the best policy, and each person has some opinion or some ideas about what is the best policy, and those are because of their private signals. So there would be some private signals with known distributions. They are informative about this best option theta, so conditional on theta they have a known distribution, and these signals are independent across different agents. So different agents have independent information, so they have an incentive to learn from each other, to know each other's private information before committing to a decision. And that is basically the incentive for interacting in a group. Agents, they start from a full support prior belief, that is for their decision making, and there is an action space that is basically the subject of the decision. They have to choose an action from this action space. And the actions are rewarded based on a utility function that is dependent on the action as well as the state of the word, the unknown state of the word. So the Bayesian heuristic framework that we propose for information aggregation, and it is information aggregation because in this group decision scenario, the externalities that agents have on each other are basically informational. The incentive to communicate comes from the fact that somebody knows something that you don't know, and therefore you have an incentive to interact with them. It is not because actions lead to a strategic interaction. So you don't necessarily need somebody to act in a particular way, but you want to know what they know, and you don't know. So in this kind of situation, the main goal is to aggregate information and come up with the best descriptor of everybody's information. And the Bayesian heuristic framework relies on real-world behavior of people, behavior such as history neglect or no recall. In many situations, people exhibit snap judgments or spur-of-the-moment behavior without evaluating their options carefully or rationally. They will just look at what there is and interpret them. Kahneman refers to this as the fallacy of what you see is all there is. So they do not root back the observations to their causes. They just regard everything as what it is. So this is a basis of fallacies such as history neglect. And it is bounded rational in the sense that the agents, when they want to make decisions, they base these decisions on simplifications of their environment. Because the original environment, its full analysis may require too much brain power, so they simplify their environment. In that sense, they are bounded irrational. So it also relates to a dual process theory of decision making. This dual process theory identifies two systems of thinking. One system that is fast and automatic. This system is the one that basically adopts heuristics and relies on heuristics for decision making. And there is another system that is deliberative, and more rational behavior can be attributed to that system. So we take these ideas and we propose the following. That in this group decision scenario, at the initiation of their interactions, agents are going to rationally interpret their observations, meaning that whatever they see from somebody, they root it back, the actions of others to their causes of those actions, and then perform a rational inference on those causes to come up with the best action, given their observations. But in future, once they have come up with this model of behavior, then their slow or deliberative system is going to be replaced by a faster system. They get used to their environment. In a sense, they learn their environment. Now the decision-making process is going to be dominated by a fast system or an automatic system that takes the heuristic form of what happened at time 1 and repeats it for future time steps. So our proposal is basically to take the Bayesian update at time 1 and use it as a heuristic for decision-making in future time steps. So to implement this proposal in various scenarios, I start with a few assumptions that lead to the Groot model, that the averaging rule that I described at the beginning. The assumptions that we need are threefold. First, we need the likelihood of the signals to belong to the exponential family signal structure. The exponential family is a very common family. Many of the known distributions belong to that. Gaussian signals with Poisson signals, all of them belong to the exponential family. And we need their beliefs or the priors that they have to be conjugate to those exponential family likelihoods. Conjugacy is another property in exponential families, and different members of exponential family show this conjugacy, meaning that once you start, for example, from Gaussian and Gaussian signal, and your belief is Gaussian, once you do the Bayes update, you come up with a Gaussian belief. So structure is preserved. And this comes from the fact that Gaussian distribution is the conjugate of itself. The same thing happens with Poisson and gamma beliefs. So if you observe a signal that has a Poisson distribution, and your belief about the parameter is belonging to the gamma distribution, then once you do the Bayes update, you get back another belief that belongs to the gamma family. So the structure is preserved, and this structure preservation goes back to the conjugacy relation between gamma distribution and Poisson distribution. Same thing with binomial signals and beta beliefs. So we need the beliefs to be conjugate to the signals, and we also use a quadratic utility. It's the natural utility. It's a minimum variance Bayes estimate about the sufficient statistic of this exponential family. So each exponential family has a natural sufficient statistic, and that is part of the basically parameterization of the distribution. I have an appendix slide at the end if you want to see the exact mathematical details of this formulation. But suffice to know that to each exponential family distribution there is a sufficient statistic, and the goal of agents in our model is to estimate the expected value of that sufficient statistic. And its expected value depends on theta. In that sense, they want to determine a function of the unknown theta. And this estimation should be with as little variance as possible. That's why it's a quadratic utility. So under this framework, we get that the action that agents takes at time 1 would be an affine combination of the actions that it observes from its neighbors at time 0, as well as its own action at time 0. So we got quite close to the structure that we were aiming for. We were aiming for a convex combination structure, an averaging rule or a weighted averaging rule, and by imposing this exponential family signal structure, the conjugate belief structure, as well as a quadratic utility, we came up with an action update that is affine. So the affine constants come from the priors that the agents have. And the good question is, if they repeat this affine action update, how would their beliefs evolve, or how would their actions evolve? And the answer would be given by the theory of positive linear systems. But in particular here, since it's an affine action update, we get a non-homogeneous positive linear dynamics, and there would be a limit to these actions whenever the spectral radius of this matrix of coefficients to these affine updates is strictly less than 1. And they would be basically the action updates would be divergent. There would be multiple fixed points if the spectral radius is equal to 1, and it would be an unstable dynamics with actions going to plus or minus infinity if the spectral radius is greater than 1. So we don't get consensus. We may not even ever get convergent behavior, and at some circumstances we will get convergence to plus or minus infinity. That's basically convergence to extreme options. Yes. Yes, it's time invariant because the coefficients come from the coefficients that were assigned at time 1. But if they were going to be rational, one way of interpreting the update rule would be to have time varying coefficients. And the fact that these coefficients are not time varying, that is one way of looking at how they are deviating from rationality. So to get rid of these affine constants, we need to have non-informative priors, meaning priors that do not influence actions. Non-informative priors, a good example would be, for example, a uniform prior that doesn't give you data. That's true for a beta distribution, actually. When your signal is a binomial signal, so your priors or your beliefs would belong to the beta distribution family, and the non-informative prior in the beta distribution is a uniform 0-1 distribution. For any class of distribution, you can single out an element of that class that is non-informative in the sense that it won't influence your action or your base update. So once the agents start from non-informative priors, then their action updates would become linear action updates. So we lose the affine constant. The affine constant would be 0. And this time we get a homogeneous positive linear dynamics. If the spectral radius of the coefficients are 1, the group is what we call a depolarizing group, meaning that the agents reach a consensus on a middle action. If the spectral radius is 1, the action converge to a fixed point in the convex hull of the initial actions, but that fixed point does not necessarily indicate a consensus. And if the spectral radius is strictly greater than 1, then the system is unstable. The actions are going to converge to plus and minus infinity. This is a case of a polarizing interaction between the agents. Their choices are going to converge to the extremes. Still, we are not exactly in the de Groot model case, because in the de Groot model, when you look at this matrix of coefficients, each row has to sum to 1. Basically, we need a row stochastic matrix of coefficients. To get a row stochastic matrix of coefficients, we need to impose some additional assumptions on the model. The assumption basically would be that the signals should have the same distribution, and only the number of samples among different agents is allowed to be different. So we need a strong kind of homogeneity in the signals that agents are observing. For example, it's only the number of signals that different agents had observed that could be different. It shouldn't be that one agent is observing signals that with a different accuracy or has a greater observational ability than others. So for the Groot model to be driven as a consequence of our assumptions, we need a strong homogeneity or a kind of social harmony among the agents in the sense of their observational abilities. If we assume that the distribution of signals among the agents are identical and only the number of signals that different agents had observed are different from each other, then we get a convex combination as the action operate as a result of Bayesian heuristics. And using this convex combination, the actions are going to converge to a consensus. So asymptotically, all agents will take the same action. Now the question is this consensus action the best action given the initial observations of all agents? If it was, then it means that by interacting with each other, following these Bayesian heuristics, they have been able to come up with an action that best describes everybody's information. But this actually is rarely true. The necessary and sufficient conditions for a consensus to be efficient or to be optimal under these circumstances involves very strict conditions on the structure of the network. In particular, among all connected undirected social networks, so if we restrict attention to undirected relations such as friendship when it is bidirectional, then only complete graphs can lead to efficient consensus. So we need all-to-all communications for the consensus to be efficient. And this is something that is quite reasonable. It's roots back to groupthink and group polarization and all the inefficiencies that are associated with group interactions. Basically, efficiency is too much to expect from agents that behave in such a naive way, because they cannot interpret the actions of others, and they are prone to repetitions as well as structural effects in the network. Most significantly, if somebody in the network is located in a very central position, then that person's actions and opinions is going to play a major role in shaping the consensus action. And this major role is because of its location rather than the quality of their observations. So the share of people in shaping the consensus action goes back to how well connected they are rather than how good the quality of their observations are. Many results in the literature have referred to different variations of this phenomenon. Like, for example, persuasion bias refers to the fact that people in a social network are prone to receiving several copies of the same report of a faraway agent. Therefore, they are persuaded by that agent because they cannot compensate for these repetitions. And there are other examples that point out these structural effects that are associated with the naivety of agents. So this was the kind of insight that we get from a linear model. Now let's look at another class of conditions and another scenario for communication. Here, instead of a continuous state space, we look at a finite state space, so there are only m possibilities. And then we suppose that agents are taking actions over the probability simplex on this m state. So their actions are probability distributions. And the utility that rewards their action is a quadratic utility that measures the distance to the true state. So they are motivated to basically announce their beliefs truthfully under these conditions. What's happening is that agents are simply exchanging their full beliefs with each other. It's a rich information scenario compared to the previous case. In the previous case, agents interact by taking actions, whereas here they are revealing their beliefs completely. So under these circumstances, we can follow that framework of driving the time one Bayesian update and analyzing its structure. The time one Bayesian update in this case has this multiplicative structure. To understand this equation better, for example, you can assume that the agents are starting from uniform priors, so that the priors are going to be cancelled out. Then what it's prescribing is for the updated belief to be proportional to the product of your own as well as your neighbor's beliefs. So it is a simple product rule for belief updates. That is the kind of heuristics that we get when agents are exchanging beliefs with each other. At the first sight, it may look quite different from the linear action update that we saw, but actually we can impose an algebraic structure on the beliefs so that we recover the same addition and subtraction that we had. If you define addition of two beliefs as such by the product of by their normalized product, then over the interior of probability simplex, the beliefs will form an abelian group. Group, I mean in the sense of algebra, not group of people, because it has the closure, associativity, and commutativity properties. It has an identity element that is the uniform distribution. It would be its identity. Each element has an inverse, and now that you have an inverse, you can also, and since you have commutativity, you can also define subtraction of two beliefs. And under these group operations, addition and subtraction, the belief update that I had written would be summarized as follows. You sum the beliefs of your own and neighboring beliefs, and then you subtract for the prior of your neighbors. You compensate for their priors. You can also have the nth power of mu by defining the power operation, basically addition of mu with itself. This operation would happen to be distributive, would show distributive properties. So if you have a sum of two numbers n and m, then it would be the addition of two integers would be distributive over this power operation. And this allows us basically to write down the belief updates for the whole network in this matrix format. And this in turn allows us to analyze what happens to the beliefs at time goes to infinity. We just need to apply the Perron-Frobenius theory to this non-negative matrix, that is identity plus the adjacency of the network. asymptotically, as time goes to infinity, the powers of a non-negative matrix would be convergent to, would basically be dominated by its spectral radius, and it would be convergent to a rank 1 matrix, that is the product of the left and right eigenvectors corresponding to the spectral radius. And asymptotic beliefs can be analyzed using these techniques. The result is that asymptotically, if the agents set their beliefs proportional to the product of their own and neighboring beliefs repeatedly, these beliefs are going to converge to basically the asymptotic belief would be concentrated, and the support of the asymptotic belief is this set of all maximizers of the likelihoods of initial signals. So this is a very good thing in some sense, because you are converging to a maximum likelihood estimator. There are some caveats here. First of all, these likelihoods are weighted, and the weights are coming from the left eigenvector corresponding to the spectral radius. It is sometimes called the centrality of the agents. The weights come from the location of the agents, how central they are. So if somebody has received some signal, just because their location is more central, that signal would have a greater effect in determining the support of the asymptotic belief. And if the maximizer is unique, then the belief would be a point mass that is concentrated on that unique maximizer. You need maximum likelihood estimator. What is the weighted maximum likelihood? The weights would be equalized in very symmetric structures. For example, if the graph is degree regular, so everybody talks to the same number of people and hears from the same number of people, and balanced, then in such structures, in such highly symmetric structures, everybody would have the same centrality, and the beliefs would be basically concentrated on the maximum likelihood estimator. In that sense, those highly symmetric group structures are more efficient. But there is a major difference between the asymptotic belief that comes out of the Bayesian heuristics and the optimal belief of a Bayesian agent with access to the initial signals. It comes from the fact that asymptotically, after interacting through Bayesian heuristics, the agents are rejecting a lot of possibilities because they put zero mass there, and the asymptotic belief is concentrated on the maximizers of the likelihood, rather than putting a higher probability on those maximizers and less probability everywhere else, as a Bayesian agent would do. Their behavior is quite extreme. They reject the possibility of any less probable state and put all of the probability mass on those maximizer states. That is another way that group polarization demonstrates itself in this rich information belief communication scenario. This overconfidence in group aggregate, people thinking that the more probable state is certainly true, rather than just thinking that it is more probable. So to recap the conclusions, in the first part of the talk, we saw how the group model would come up as a consequence of assumptions such as history neglect and snap judgments, assumptions that are associated with the automatic decision-making system, and they are observed in real-world behavior as a simplification of the environment, as a bounded rational behavior. But it's not just the no-recall assumption. We needed some additional assumptions to get the exact deGroote model. Assumptions such as non-informative priors, so agents should base their reports on their purely signals, not their biases. And to get exactly the deGroote models, to get a row stochastic matrix of coefficients, we need the agents to have very similar observational structures. So the signals that they observe should have identical distributions, and the only difference could be in the number of samples that they observe from that distribution. Otherwise, we cannot satisfy the requirement of row stochasticity for the matrix of coefficients. We also saw several arguments for the inefficiency of this heuristic decision-making behavior. Inefficiencies that, such as group polarization and the vulnerability of agents to structural effects and persuasion by well-connected agents in the network. So one good advice would be to inform people about these effects and the advantages of rational decision-making that may avoid these inefficiencies. And we also observe some key differences between belief updates that are derived through Bayesian heuristics and the action updates. If we have the possibility of implementing belief updates, then belief updates would be much more robust. First of all, they are unweighted and they are symmetric, whereas the action updates, the actions are weighted based on the quality of the signal of each of the agents. The beliefs internalize the quality of the signals, so the belief updates are unweighted. And they can effectively compensate for the priors, so it doesn't matter that the agents may start with some priors. The multiplicative belief updates can effectively cancel out the priors, whereas for the action updates we needed to assume that agents will have non-informative priors. Otherwise, the effect of these priors would accumulate at every time step, and the actions can grow to extremes. So, yes, thank you for your attention. That's it. If there are any questions.
So in the cases where, I guess I have two questions. In the cases where you're let's say in the first algorithm that you have the linear one,
Mm-hmm.
the update doesn't convert, diverge to infinity. When does that happen? Like, can you give
Yes, we can.
simple examples where this is?
We can characterize the convergence mathematically. So it all depends on the spectral radius of the matrix of coefficients. In the non-homogeneous case, when the priors are existent, so we don't have non-informative priors, in that case, it is these constant terms can accumulate. So we need a spectral radius that is strictly less than 1, and then the asymptotic action would be basically is the solution of this matrix inversion. Asymptotic action, first of all, it is not a consensus. There's no reason for people to be convergent on the same action, and it is primarily determined by the priors. So rather than aggregating information, the agents are driven completely by their priors. If the spectral radius is 1, then we get oscillation between different fixed points, because basically this spectral radius being 1 is pointing out to a linear system having multiple solutions. And if this, for this non-homogeneous case, and if the spectral radius is greater than 1, that is where we get convergence to extremes, plus and minus infinity.
When does this spectral radius that is larger than 1,
Mm-hmm.
can you give some example where this is happening? Like, what are the conditions of the
Mm-hmm.
signals and the priors or the connectivity of the graph?
Yes, I have thought about this myself, but it's not an easy task to relate the spectral radius of matrix of coefficients to the properties of individual agent signals or even the structure of network. Relating it to the structure of networks is easier because the spectral radius is a global property, so it is more I mean, it's easier to imagine, for example, in special conditions when the agents are receiving IID signals and just one IID signal, not different number of signals, then you can give conditions for the spectral radius to be greater than 1 in terms of the structure of the network. But giving conditions in terms of the properties or signal structure of individual agents is much harder because it is not a local property.
And then in the case where it converges to that limit,
Mm-hmm.
do you have you thought about the inefficiency of that limit point? With respect to, compared to the case where you have all the signals available to be given.
So it is extremely inefficient, right? Because the efficient action it's clear what it is. It is basically you take all of the signals, you do the base update given all these signals, and then you have an estimator. That is a point on the real line, and if the outcome of decision is plus infinity, it means that basically it's failed. But it can happen. I mean, yeah, it is a case of choice shift toward extremes. I mean, in practice, you see people interacting with each other and then thinking very extreme, ending up with any extreme opinions.
So, are there any other questions? If not, we can thank Amin one more time.
Thank you.